Hello, my dear students. Welcome to the session. Continuation of important observations from power electronics concepts. I'm discussing power semiconductor devices concepts. Now we have to start with the calculation of switching losses. Students, we know that in any switch, during switching, there exists a two types of losses. One is turn on switching losses. Another one is turn off switching losses. Turn on is characterized by rise in current. That is, during turn on, current is rising, fall in voltage. Voltage is falling. This is also important observation. During turn off, voltage is rising. That is, voltage across the switch is rising, current through the switch is falling. This is how to characterize turn on transition and turn off transition. To calculate the turn on energy loss and turn on power loss. Similarly, to calculate turn off energy loss and turn off power loss, first we have to know what is the voltage and current equations during turn on transition and turn off transition. This is the current equation during turn on transition. This is the voltage equation during turn on transition. Once you know this current equation and voltage equation during turn on transition, similarly you have to calculate what is the current equation during turn off transition, and this is the voltage equation during turn off transition. By knowing these values, now we have to calculate on-state switching average energy loss. But these formulas are applicable with the assumption of during on-state linearly current rising. For this type of characteristics only, these formulas are applicable. During turn on, voltage is falling. That is linearly voltage is falling. That is linearly current is rising, linearly voltage is falling. Then what is the on-state average energy loss? This is the direct formula that you have to concentrate. 1 by 6 Vi into T on. Once you know the energy loss, then how to calculate the power loss? Students, we know that energy equal to power into time. Then power equal to energy by time. 1 by time is written as a frequency. That is energy into frequency. This is the on-state switching energy loss. Then what is the on-state switching power loss? On-state switching power loss is, that is 1 by 6 Vi into T on into F students. That you have to concentrate. The energy loss is, here there is no any frequency term, but here we are getting frequency term. This is energy loss and power loss calculation during on-state. Then what is the off-state switching average energy loss? Here extra we can get 1 by 6 Va into T off. Previously T on, this is T off. But how to characterize the off state? I told already, current is falling. During off state, current is falling, voltage is rising. And this formula is also applicable linearly falling and linearly rising characteristics. If they given different characteristics, according that only how to calculate. But if the characteristics are given like this, no need to calculate separately, directly you apply the formulas. This is during off state energy loss. Then how to get the power loss? Into frequency. This is the off state power loss. Once you know the on state energy loss, off state energy loss, on state power loss and off state power loss, then we have to calculate total average energy loss. This is the final formula that you have to concentrate. And once again I am repeating, these formulas are applicable only for linearly rising and linearly falling. This is the total average power loss. 1 by 6 Vi into T on plus T off into F. See what is the difference here? Energy loss and power loss. In energy loss there is no frequency term, but in power loss there is a frequency term. What is F here? This F is the switching frequency. That you have to concentrate. F is the switching frequency. Switching frequency. And this F equal to 1 by time period, that you have to write. 1 by, that is T is nothing but a T on plus T off. T on plus, that you have to consider. This is the calculation of switching losses during turn on transition and turn off transition. How to characterize the turn on transition? Current is rising, voltage is falling. How to characterize the turn off transition? Current is falling, voltage rising. Based on this concept, and one more important point you have to remember here. What the peak instantaneous power loss? Instantaneous power loss is nothing but instantaneous voltage into instantaneous current. This gives the instantaneous power. What the condition for peak instantaneous power loss? This is the condition for peak instantaneous power loss. Then what is the formula for peak instantaneous power loss? The peak instantaneous power loss equal to 1 by 4 into V. This also you have to concentrate. And this formula is also applicable only for linearly rising and linearly falling. This is the formula for peak instantaneous power loss. That observation is also very important. And based on this concept, I solved one model of question here. You please practice this question. Here for this characteristics, it is asking that what is the energy loss? Is it a turn on transition or turn off transition? That also you have to observe from this given character, identify from this given character. It's easy to identify. Current rising, voltage is falling. Current rising, voltage falling. Then what is this transition, friends? It is a turn on transition. But whatever the characteristics here it is given, if voltage is constant, current is changing. If current is constant, voltage is changing. But it is not linearly rising and linearly falling, both at a time. That's why whatever the previously I derived the formulas, that formulas don't apply here. You have to calculate separately. Then what the energy equal to integral Vi dt. This is the fundamental formula for energy loss. During T1 time, which is constant, students, voltage is constant. Then I dt plus during T2 time, which is constant, current is constant. Voltage is changing, integral V dt. Integral I dt is area under the current curve, students. You have to find the area under this curve of I into T1. During T2 time, which is changing, voltage is changing. You have to find area under this voltage curve of T2 into V. And finally, we can get this one. But what is this transition? It is a turn-on transition. Because current through the switch is rising, voltage across the switch is falling. That's why it is a turn-on transition. What is the energy loss? This is the formula for energy loss that you have to concentrate. Then same concept you have to apply here. Then one more problem that I solved. Please go through this one. This is the previous gate question. This is a PYQ. Previous gate question that you have to. Here also same concept. Voltage is constant, current is changing. Current is constant, voltage is changing. That is integral Vi dt. Voltage is constant, current is changing, integral I dt. Integral I dt is area under the current curve. What is the area under the current curve? Half BH now. Half into B is 1 microsecond. H is this total is H, friends. 100 into 100 plus 50, 150. Plus during T2 time, next 1 microseconds of time, which is constant, current is constant. How much current is constant? Only 100 ampere amplitude. Na? Then which is changing? Voltage changing. Area under this voltage curve, half into B into H. That you have to calculate, simplify this. We can get 75 millijoules. This is about the concept of how to calculate the switching law. And one more important concept with respect to semiconductor devices concept, that is the construction of the power diodes. Construction of power diode. Construction of power diode. This is also very important. With respect to construction of power diode, mainly you have to concentrate two important points here. In a power diode, extra n minus layer is present. This layer is called intrinsic layer. What this n minus layer is called? Intrinsic layer. Intrinsic layer. Then what is the purpose of using intrinsic layer? This intrinsic layer supports high blocking capability. This is very important. It supports high blocking voltage. High blocking voltage. Generally, diode is how many layers? It is a 2 layers. But if the question is asked about the power diode, friends, if the question is asked about the power diode, but power diode is a 3 layer. But remaining points are normal diode and power diode is same. Extra 1 point it is added 3 layer device. It is not a 2 layer device. But what is this 3 layer extra layer? N minus layer. This N minus layer is called intrinsic layer. A lightly doped N minus layer is called intrinsic layer. That's why this diode is also called pin diode. But because of this extra layer, there is no formation of extra junction. But it is having only one junction. Even though it is a power diode, it is one junction only. It is a 2 terminal only. It is a bistable only. It is a unipolarity, unidirectional, uncontrolled device. But only different from actual diode, power diode is n minus layer. This is 3-layer device. That point you have to remember. This type of structure is called vertically oriented structure. Because of this vertically oriented structure, the power loss is less. And one more reason why the power loss is less in a power diode, because of conductivity modulation. The 2 points also very important. A vertically oriented structure is preferred in all the power devices as it increases the surface area for the forward current, therefore reduces the forward resistance and state power dissipation. Due to conductivity modulation, power diodes offers less power loss. Why the power diode offers the less power loss? Because of the conductivity modulation. This point you have to remember with respect to power diode. And what the purpose of using intrinsic layer? The intrinsic layer supports the high blocking voltage. The 2 points are very important. And because of vertically oriented structure also, the power losses are less. Very important, students. Vertically oriented structure is not supports the high blocking voltage. N minus layer only supports the high blocking voltage. Yeah, that points mainly you have to concentrate. Here I solved the one question. You please go through this one. A structure obtained by lightly doped N-drift region between the N layers of PN junction. A pin diode is obtained. This structure is effective in making the diode supports large reverse blocking voltage. Because of N minus layer only, it supports the high blocking voltage. Next. One more important concept with respect to diodes, that is the characteristics of a diode. With respect to diode characteristics, turn on behavior and turn off behavior. A turn on behavior not that much of important, but turn off behavior characteristics are very important. Yeah, this you have to concentrate what are the typical values, that is the VFR called forward recovery voltage 10 to 30 volts. This point mainly you have to concentrate. In a diodes, what is the forward recovery voltage? What is the forward recovery time in the range of 10 microseconds? These 2 points mainly concentrate. Then how to calculate the average power loss. But reverse recovery characteristics of diode is very. With respect to reverse recovery characteristics of a diode, you have to concentrate how to define the reverse recovery time. One definition for reverse recovery time is the time taken for reverse recovery current. And one more important, based on this definition, already question is there in competitive exam. It is the time between at the instant of forward current 0 to, that is where the forward current is 0. From that instant, this forward current falls to 25% of maximum value of reverse recovery current. That is, whatever this reverse recovery current is there, this reverse recovery current falls to 25%. Whatever the time is taken, that time is called reverse recovery time. This reverse recovery time is very important to select a diode for particular application. The diode which is designed for high reverse recovery time, that is used for low frequency application. The diode which is designed for low reverse recovery times, that is used for high frequency application. Very important. If TRR is less, the diode which having the less reverse recovery time, that is used for the high frequency application. These relations also you have to concentrate. The total reverse recovery time equal TA plus TB. Here I given the what is the significance of TA and what is the significance of T. During TA time, stored charges in the layers are removed. During TB time, stored charges at the junctions is removed. This is a reverse recovery characteristics that you have to concentrate. But very important is definition you concentrate. From this reverse recovery characteristics, very important formula, we are calculating stored charge. What is stored charge? QRR. What are the QRR, students? QRR is the stored charge. Very important formula that you have to concentrate. Stored charge. That is 1 by 2 IRM into TRR, where TRR is the reverse recovery time, IRM is the peak value of reverse recovery current. Yeah, these terms I given here. IRM is the peak value of reverse recovery current, QRR is the reverse recovery charge, di by dt is the rate of fall of diode. This is one formula for QRR, and this is the IRM formula. IRM equal TA into di by dt. But point you have to remember, this is the exact formula for IRM. This is the exact formula. Exact formula for IRM. But sometimes this IRM is also nearly equal TRR into di by dt. But now the question is, when you can apply this formula, when you can apply exact formula. If the TA data is available, then go for this formula. If TA data is not available, then go for this formula for approximate. Okay, these two observations are very important that you have to concentrate. Here I given IRM equal TA into di by dt. This is the exact value. IRM is nearly equal to TR into di by dt. This is approximate form. Then QRR equal to 1 by 2 into IRM into TR. This is the exact form. This is the approximate formula for QRM. That is the QRR, not only QRM. This is equal to QRR. Equal to QRR. Here I am defining the one factor that is called softness factor. What is the softness factor? TB by TA is called softness factor. Based on the softness factor, the diodes are classified into two types. If the softness factor is greater than or equal to 1, those diodes are called flow recovery diodes or soft recovery diodes. For those diodes, reverse recovery time is very high. That's why it is used for low frequency application. The diodes which having the softness factor is less than 1, those diodes are called fast recovery diodes or snappy recovery diodes or transient recovery diodes or abrupt recovery diodes. These are used for the low turn off time application. Low turn off time means whose reverse recovery time is less. The turn off time is less. For those applications, we are using the fast recovery diode. This is based on the softness factor. Based on the softness factor, how the diodes are classified, soft recovery diode and fast recovery diodes. That you have to concentrate. And one more important note point you have to remember here before solving the problem. There is one diode is there, Schottky diode. This is also very important. Schottky diode. A Schottky diode is a combination of metal plus semiconductor layer. It consists of aluminum and N layers. This is important. We know that in most of all the diodes, the combination is all are semiconductor layers. But this is the combination of metal plus semiconductor. Metal plus semiconductor. The metal plus semiconductor that you have to concentrate. Which is the metal? Aluminum is the metal, semiconductor layer is the N layer. Friends, we know that in aluminum, which are the carriers? Electrons are the carriers. Electrons are the carriers. In N layer, which are the carriers? Electrons are the carriers. That's why a Schottky diode is a majority carrier device. The total conductivity is due to only electrons. This is also important. It is a majority carrier device. That is a unipolar device. Majority carrier device. Carrier device. That is a unipolar device. Unipolar. The total conductivity is due to only electrons. The total conductivity due to only electrons. Only electrons. That point you have to remember. And what about the Schottky diode? This is used for high frequency application. Used for high frequency application. At this point also you have to remember. As compared to Schottky diode, which diode is used for high frequency? Silicon carbide diodes. With respect to frequency of operation, silicon carbide diodes are used for ultra high frequency application. Silicon carbide diode is used for ultra high frequency application. The Schottky diode is the metal plus semiconductor. And one more point you have to remember in diodes, which diode is having the negative resistance characteristic? Tunnel diode is a negative resistance. Gun diode is also negative resistance characteristic. You already know UJT is also negative resistance characteristic. Yeah, this also you have to remember as a note point. This also I am giving as a note point. One is that is tunnel diode. Tunnel diode. Tunnel diode. And gun diode. Gun diode. And UJT. Unijunction transistor. These are having which characteristics? Negative resistance character. Negative resistance character. Here I solve some problems that you have to concentrate. A power diode in the forward conduction mode and the forward current is now decreased. The reverse recovery time of the diode is Tr and the rate of fall of diode current is di by dt. What is the stored charge? I already given the stored charge. Approximate formula for stored charge is that is 1 by 2 di by dt into Tr square. Di by dt into Tr square. 1 by 2 is the 0.5. This is the answer. And the reverse recovery time of diode is 3 microseconds and rate of fall of diode current 30 ampere per microsecond. The stored charge. But here there is no data for to calculate the TA. Then stored charge equal to approximate formula you have to apply 1 by 2 di by dt into Tr square. That is the 135 microcoulombs we can get. Please go through this problem. Then I already given the what is the definition of reverse recovery current. It is fall to 25% of IR. That is the reverse recovery time. Reverse recovery time definitions. Then here I solved one problem based on the calculation of average power loss during on time. During on time. I given already turn on characteristics and turn off characteristics. This please go through this problem also. This is the calculation of average power loss during conduction of the diodes. And this also important. Here you know the TA data by knowing the softness factor. I calculated TA. Once I know the TA, then you apply the IRM formula is TA into di by dt. This is important. Don't apply IRM equal TRR into di by dt. Why? I know the TA data because softness factor is given. From that softness factor, I calculated TA. Once you know the TA, apply the IRM TA into di by dt. From that, I calculated IRM value. Once you know the IRM value, then this is the exact formula you have to substitute. Then you can get the what is the reverse recovery charge. These models of questions also you have to practice. Next, with this diode concept is completed. How to calculate the switching losses also completed. And one more important concept with respect to power semiconductor devices concept, that is the thyristor concept. SCR I am going to start in SCR or thyristor. SCR, that is a silicon control rectifier. Is a thyristor I am going to thyristor. For thyristor, so many concepts are there. Important points only mainly we are concentrating because this is the quick revision of the power electronics concept. Yes. With respect to construction of the thyristor, mainly how to concentrate it is a thyraton and a transistor. It is a combination of thyraton and transistor. The thyraton is a type of gas filled tube that also you have to concentrate. Then SCR is how many layers? It is important. It is a 4 layer, 3 junction, 3 terminal, bistable, semi control, positive feedback, latching device. This is important. SCR is a latching device. It is a latching device. It is a semi-control device. Why it is a semi-control device? Turn on by gate, but it is not turn off by gate. That's why it is a semi-control device. And it is a latching device. In SCR, internally positive feedback action is takes place. How many layers it is having? 4 layers. How many junctions? 3 junctions. Anode, cathode and gate. How many terminals? There is a 3 junction. J1, J2, J3 is a 3 junctions. How many terminals? 3 terminals. Anode, cathode and that you have to consider. This J1, this is J2 and J3 junction. This J2 junction is also called gate junction. J1 junction is called anode junction. J3 junction is called cathode junction. With respect to SCR, modes of operation is very important. That before going to that one, you have to concentrate what the doping of different layers in SCR. N2 is heavily doped thin layer. The doping concentration is more, thickness is less. P2 is the less heavily doped thicker layer. N1 is the less doped thickest layer. And P1 is the same that of P2. These are the doping concentration of different. These are the some differences between SCR versus ASCR. ASCR is nothing but asymmetrical SCR. SCR stands for asymmetrical SCR. Please go through this point. Here summary point I given. You please concentrate here. SCR and ASCR. Forward blocking voltage is high in SCR. ASCR is also high. Reverse blocking voltage is high in SCR, but it is very low. Turn off time is high in SCR. Turn off time is low. This is the advantage. SCR is designed for low turn off time. Voltage drop is high in SCR. Voltage drop is less in ASCR. Because of turn off time is low, then this is used for the high frequency application. ASCR is used for high frequency application. This is for low frequency application, and this ASCR is used for high frequency application with respect to SCR and ASCR that you have. With respect to symbol point of view, this is a thyristor symbol that you know all of you. Or the thyristor symbol, the SCR symbols. But what about the ASCR symbol? This is asymmetrical SCR. But only main difference is blocking voltage capability. The blocking voltage capability is different. Forward blocking capability is same, but reverse voltage blocking capability is different. That is the main difference. Because of less, it is designed for less reverse blocking capability. Because of change of doping concentration, then it is used for the high frequency application. This is a structure point of view. This is for ASCR structure and this is for SCR structure that you have to concentrate. Then some differences also I given. Please go through this. Next, very important observations. What are the modes of operation and static VI characteristics of SCR? Friends, we know that SCR is operated in three modes of operation. It is operated in three modes of operation that you have to concentrate. One is reverse blocking mode, forward blocking mode, forward conduction. In reverse blocking mode, anode to cathode voltage negative, forward blocking mode, forward conduction mode, anode to cathode voltage. In reverse blocking mode, which junctions are reverse bias, which junctions are forward bias? That is important. Under reverse blocking mode of operation, J1, J3 reverse bias, J2 is forward. J1, J3 means the statement we can also expect like this: outer junctions are reverse bias and inner junction is forward bias. Outer junctions are nothing but anode and cathode junctions are reverse bias. Like this, any statement we can expect. In the framing of the question, they will give the name J1, J3, J2 junctions. They will give the name outer junctions. They will give the name anode and cathode junction. Like that also we can expect. But here, reverse blocking mode, which junctions are reverse bias, which junctions are forward bias, that you have to concentrate. Under reverse blocking mode of operation, among all the junction, which junction blocks the high voltage? J1 blocks the high voltage. Next, J3. But J2 blocking capability is negligible because it's already closed. Because J2 is forward bias condition. This is under reverse blocking mode of operation. These are the static VI characteristics of SCR. This is for reverse blocking mode. This is for forward blocking mode. This is for forward conduction. In forward conduction mode, latching current and holding current observation is important, that I will explain. In reverse blocking mode, highest voltage is reverse breakdown voltage. In forward blocking mode, highest voltage is forward breakdown voltage. Then in forward blocking mode, which junctions are forward bias, which junctions are reverse bias? J1, J3 is forward bias, J2 is reverse bias. That is, J1, J3 means outer junctions are forward bias, inner junction is reverse bias. And one more important observation, because of J1, J3 is forward bias, these two are acting as one conducting plate. This is one conducting plate, this is one conducting plate. Because of J2 is reverse bias, it is open switch. J2 reverse bias means open switch. It acting as a dielectric medium. Two plates are separated by dielectric medium. That's why under forward blocking mode, SCR is equivalent to capacitor. Under forward blocking mode, SCR is equivalent to capacitor. Here I given when a thyristor is negatively biased. Negatively biased means reverse blocking. Outer junctions are negatively biased and inner positive. Positively biased means forward bias. Negatively biased means reverse bias. Like that you have to remember. When a thyristor is in the forward blocking state, anode and cathode junctions are for, that is outer junctions are. Inner junction is reverse bias. These observations are important. Next, forward conduction mode. Very important. To bring the SCR into forward conduction mode, you have to apply the gate signal. After applying the gate signal, the J2 junction is also closed. Then if the SCR is under forward blocking mode, all the three junctions are forward bias. That is very important. If the gate supply is given, more number of charge carriers are injected to J2 junction, and due to this, J2 width is reduced with less forward voltage. J2 is breakdown and here comes conduction. If you draw the characteristics between gate currents versus forward voltage, if the gate current is increases, forward voltage is reduced. Gate current is increases forward. This is the relation. Higher the gate current, less will be the forward. But even though gate is connected, a minimum forward voltage is required to bring the SCR into conduction mode, friends. That minimum forward voltage is nothing but a finger voltage that you have to consider. During the conduction of SCR, this is important. 5-star point. This already framed in gate exam also. During the conduction of SCR, all the three junctions are forward. But in forward blocking mode, reverse blocking mode is different. But in during conduction of SCR means during conduction mode, all the three junctions are forward bias. All the three junctions are forward. At the time of removing the gate supply, anode current in the SCR must be reach a minimum value of current, that is called latching current. That is, latching current is associated with the turn on process. Once SCR start the conduction, no use of gate switch. Then you can remove the gate signal. But at the time of removing the gate supply, the anode current to the SCR must be reaching to some minimum value of current. After reaching that current only, you can remove the gate pulse. That current is nothing but a latching current. If gate supply is removed before anode current is rising to latching current, again SCR automatically comes into blocking mode. It will not enter into. That's why latching current is associated with the turn on process. This latching current is reference for turn on of SCR. Then what is the holding current? To turn off the SCR, we have to reduce the anode current below some minimum value of current. How we can reduce the anode current below some minimum value of current? By applying the reverse voltage. That current is nothing but a holding current. This important observations. Always latching current is greater than holding current. In general, latching current equal 2 to 3 times of holding current. If it is not given, you take the latching current equal to 2 times of holding current. In average, latching current equal to 2.5 times of holding current is associated with the turn off process, important. But latching current is associated with the turn on process. Here I given some important observation that you have to concentrate. Even though gate is connected, a minimum forward voltage is required to bring the SCR into forward conduction mode. It is called finger voltage. That means we know that if the gate current is increases, forward voltage is required. That forward voltage required is reduced. But is it possible to bring the SCR into conduction mode without any forward voltage? Not possible. Even though you connect gate, you must apply some minimum forward voltage. That voltage is called finger voltage. For reliable turn on of SCR, gate must be on minimum up to latching current. That I told already. You have to connect the gate terminal up to latching current. Up to anode current is rising to latching current. Don't remove the gate before anode current is rising to latching current. That's why this is important model. Sometimes in the problems what it is asking, for reliable turn on of SCR, what is the minimum gate pulse width they are asking. To solve this type of models of questions, just find the time corresponding to latching current. That is the minimum gate pulse width. Here one more point. Even though gate supply is connected, SCR is not triggered. Maybe due to what may be the reasons. They connected the gate, but SCR is not triggered. What may be the reason? Maybe SCR may be reverse bias. Under reverse bias condition, even though you can connect the gate, it will not turn on. That may be the one reason. You are removing the gate supply before anode current rising to latching current. I told already gate must be connected up to latching current. Na? If you remove the gate supply before anode current rising to latching current, then also SCR is not turn on, even though gate is connected. And SCR may be under reverse blocking. Then forward voltage across the SCR must be greater than finger voltage. Then only it will on. If it is less than finger voltage, even though gate is connected, it will not turn on. This is the different reasons. Even though gate is connected, why the SCR is not turn on. Here I given one question. If the SCR is under conduction mode, all the junctions are forward. Here you have to find the time corresponding to latching current. Very simple. Simply remember, gate pulse width depends only on the inductance. It depends only on inductance. You have to apply V equal to L into di by dt. Simply you can, from this, substitute the latching current is 4 milliampere. No need to do all this derivation directly. You can also apply like this. Voltage substitute. From this you find the time. Simply remember concept, friends. Find the time at latching current. That is the minimum gate pulse width for any circuit is given. You find the time corresponding to latching current. That is the minimum gate pulse. These models of questions are very important. Repeated in gate exam. Repeated in gate exam. Yeah, this is also important. Here instead of instead of L circuit, they given RL circuit. Here I solved the two models, two methods I solved. Method one is direct method. I told already gate pulse width is independent of the resistance. It depends only on inductance. Then V equal to L into di by dt. From this you find the time. Find the time corresponding to which current? Latching current. Corresponding to which current, students? You have to find the time corresponding to latching current. Latching current is 40. Or if you want detailed derivation, then RL circuit excited with the DC supply, I equal to V by R into 1 minus e power minus R by L into T. From this equate to latching current, find the time. Then also you can get the same answer, 80 micros. But better to go for this method. Even though load is RL, students, even though RL parameters are given, no need to consider the resistance. You consider only inductance because gate pulse width depends only on inductance. Gate pulse width is independent of resistance. And one more model of question. Model is same, but only circuit is different here. Then method one only I am applying. But here two parallel branches are given. You first find the what is this current. I got this is 20 milliampere. Total latching current is 60 they given. In that 20 milliampere is flowing here, remaining 40 milliampere. Then you apply this 40 milliampere through inductor. V equal to L into di by dt. Now the current is not 60 milliampere because it's parallel branch. Current is divided. This current only you take because inductor current. Then V equal to L into di by dt. From this you find the time. That time we are getting the 200 micro. That is only concept for these models of questions. Find the time corresponding to latching current. Find the time corresponding to latching current. That is the minimum gate pulse. Here I solve the method 2 also. Detailed method 2. There also we are getting T equal to. Method 2 is RL circuit excited with the DC supply, R circuit excited with the DC. This current expression I return, this current expression I return. From that I calculated the T. But this is somewhat lengthy procedures. But want to remember, gate pulse width mainly depends on the inductance only. Because only inductance only opposes the rise of current. If in any circuit, if inductance is increases, the rise of current is reduced. That is, to rise the latching current, it takes more time. To rise the latching current, it takes more time. Then you can connect the gate for more time. Then gate pulse width is more. That's why gate pulse width mainly depends on the inductance. And here in this problem, they given the latching current. They also given the time, but it is asking that what is the R value. From that I calculate the R value. I equal to I1 plus I2. RL circuit excited with the DC supply formula. V by R into 1 minus e power minus R by L into T. R circuit excited with DC supply 100 by R square. From this I calculated. This is a gate 2 marks question. This is important model. This model also, previous model is also important. This model is also important. This is about what exactly static VI characteristics of SCR, and from that what is the modes of operation, how to solve the problems. But here you have to concentrate from the static VI characteristics of SCR, latching current level and holding current levels that I told already. This is the latching current and this is the holding current. Latching current is above the holding current. So always high latching is greater than high holding. One more important point, students. If the current through the SCR is, this is the forward voltage drop. This indicate the, this area, forward conduction mode. This area indicates the on-state voltage drop. This is forward on-state voltage drop. This is not a constant value. On-state voltage drop. In any SCR, if the forward current is increases, the voltage drop is also increased. Voltage drop across SCR is also increased. This is the increase of voltage drop. Slowly it is increased. That also you have to concentrate. This is the detailed discussion of what exactly static VI characteristics and modes of operation of SCR and its related problem. What are the problems I given, students? That problems you have to practice. And I given one more problem here. Same model, you have to find the time. V equal to L into dA by dt student. Just substitute the current, substitute the voltage, substitute the inductance, find the time. That is the time corresponding to latching current. That is the minimum gate pulse speed. And IL equal 2 times of IH. From this we can solve. Here it is asking that what is holding current. What is the holding current? It is latching current is given. It is asking holding current. This is important. SCR conducting and current to the SCR is 20 ampere. If the gate current is reduced by 1 by 4, the anode current to the SCR. Point to remember students, when the SCR is turned on, gate loses its control over the SCR. That means during the conduction of SCR, this condition is during the conduction. During the conduction of SCR, by controlling gate, we cannot control the anode current. By controlling gate, we cannot control the anode current. Controlling gate. That is, we can reduce the gate current or increase the gate current. Anode current remains same. We cannot control anode current. This observation is that you have to concentrate. Students, with respect to power semiconductor devices, up to now I explained SCR static VI character. But continuation of that, in SCR itself, so many concepts are there. I have to give brief discussion on the turn-on methods and what is the dynamic characteristics. After dynamic characteristics, I would like to discuss about gate characteristics. Then after the gate characteristics, what is the protection circuit, series and parallel connection, that is a string efficiency concept is important, and heating and cooling circuit, commutation methods, and one more important concept is firing circuits of S. That will be discussed in the next session. In that, power semiconductor devices concepts will be complete. This is about the session. Thank you.